Good morning. It is April 2nd, and this is our lesson for Tuesday. Okay, so you guys have just done 46 and 47 and worked through that. I hope you all have corrected that. I'm going to be making a concerted effort for your bell ringers to be your start being your exam review. We've got a lot of stuff to cover, and not a whole lot of time after we finish our material for the class to cover it. So just really start taking those seriously, correct them as you see how they're worked, and just let that be a slow and steady review for you to be prepared even before you really kind of start intentionally, quote unquote, studying for the exam. Okay, got a lot to cover. All right, so your homework is this sheet right here, and I want to take just a minute to go through this. Let's see if I can get this straight in your screen here. Sort of. All right, so using one of these shouldn't be difficult, and that doesn't mean we don't need to read carefully and make sure we're noticing all the things about it that we need to notice. Okay, and what I want to do is I want to talk to you about the 3 or 4 different kinds of questions you can get asked with this, point out a couple of things, and then y'all can either pause me and make sure everybody's got the same answer so that you're correct on all that, or you can wait to the end of the video and then go back over this. Just make sure everybody's got the right answers. If somebody's got something wrong, y'all help one another kindly, of course, to see where you may have gone wrong, or maybe one person only got it right and everybody else got it wrong. That's always a possibility. So just it's a good opportunity for you guys to be able to talk clearly about why you solved what you did. Okay, and so as we're looking at this, there's only a few kinds of questions that could really be asked about this. So we'll just go through a couple of them, skip down, go through a couple more, skip down, and we'll be finished with this. And y'all can check the rest on your own. Okay, how much NaCl will dissolve in 100 grams H2O at 35 degrees C? All right, so the first thing we want to do, we want to check our units over here. Okay, this is grams of solute. Remember, we had solute and solvent that we talked about before. Solute's what gets dissolved. Solvent is what does the dissolving. All right, and there's a bunch of different ways to measure that, as we'll talk about here in just a moment in 10.3. But you guys have all read it, so you know. All right, a bunch of different ways to measure that. And this chart has chosen to measure it per 100 grams of H2O. Okay, that's only one way we can talk about solubility and the ability of things to dissolve. All right, but most of these are going to be asking that explicitly in that units, so we don't need to worry too much about it because we're really just doing some graph reading exercises here. Okay, how much NaCl will dissolve in 100 grams H2O? Matches here at 35 degrees C. So we come at 35 degrees C. We find our NaCl line and see what it's doing at 35 degrees C. And it turns out that's maybe 36 grams. I picked 37 grams before, so 37 grams is what we'll say. Okay, how much NH4Cl, so that is ammonium chloride, will dissolve at 50 degrees C. 50 degrees C. Ammonium chloride, bring it over, exactly 50 grams. Okay, no problem. All right, so now note that that has asked how much, so we need to answer with grams. Now this is saying what is the solubility, so it has slightly different units. Okay, so what's the solubility of SO2 at 25? Come to 25, up to SO2, I would say 8 grams. but the solubility is actually 8 grams per 100 grams of H2O. Okay, so it talks about we've got a unit here per another unit of the solvent. Okay, all right, and so we got solubility, solubility. Now we've got a minimum temperature. Okay, so we know we want to grab dissolve 80 grams of sodium nitrate. So first of all, we need to know which one's sodium nitrate. Right here. Okay, you only got 2 sodiums that start out there, and you know that's chloride, so this has got to be nitrate, even if you didn't remember NO3 was nitrate. Okay, you want to use deduction when you can, even if you can't remember what else is going on in a problem. Okay, so we want to know what temperature we have to be at to be able to dissolve 80 grams. So we come to 80 here, we follow it across until we run into the sodium nitrate, and we see that that hits right about here. And that's more than 10, less than 15, because 15 would be right in the middle. So I'd say it's 12 or 13. And I picked 12 degrees C. Okay? All right. So then the only other one, some of them are asked in a little bit different way, but the principle is the same, so I'll let you guys check your answers on that. One of these we need to look at right here. It's 13. What's the solubility of potassium chlorate in 50 grams of water at 35 degrees C? All right, so what's our let's get our solubility off here. Potassium chlorate. So where's that? Potassium, that's potassium nitrate, potassium chlorate. Remember that if it's just KCl, it's potassium chloride. So this is potassium chlorate right here. All right, we need 50 grams of water at 35 degrees C. So 35 degrees C, it's at a rate of 37 grams. Remember what our units are here. Okay, we're not just reading it per 100 grams of H2O. But what did it ask for? It asked for 50 grams. Okay, so that's an easy conversion to do because it's 100 down to 50, so it's just 1/2. But more robustly, we might want to do it like this. So we know we have 37 grams for 100 grams H2O. And so what we're doing is we're saying keep that ratio the same and just convert it to a different amount. Okay. So then what do? That times that equals this. So 37 times 50 is equal to 100x. We multiply this, we divide this over, and we end up with 18.5 grams. Okay. You say, oh, I could have just divided by 2 there. Well, that's fine, except what if it had been 40 grams? Okay, or 37.5 grams. Okay, you got to actually set up the ratio so that you can solve in any situation what you've got to do. All right, so y'all, before the end of class, make sure you do the rest of that. While we're fresh and not tired of me talking, not that you could ever get tired of me talking, of course. I appreciate it, guys. That's sweet of you to say. All right, I want to talk about the quiz and what it's going to be like. All right, so let's use our powers of deduction here and think. All right, so I try to always have math on a quiz, okay, but that's not really going to be possible here. Why? Because this is all vocabulary, okay? So you hopefully went through, and as we were talking, you were highlighting, okay, in a way that I was. All right, and I would suggest that anything you saw highlighted or highlighted yourself, of course those videos are still always available for you on YouTube. Make sure you have it highlighted, and make sure you can do 2 things. Make sure you can go from that word to a definition, or from a definition back to that word. Okay? And the way I did this throughout high school and college, you just need to make sure that you have them on flashcards, and you can do flashcards forwards and backwards. Okay, so I recommend that, and I hate to just have just a dull vocab quiz, but we've got a lot of stuff in here: dissolution, solvent, solute, universal solvent, miscible, dissociation, ionic compounds, acids, bases, hydration, polar and nonpolar, solvation, okay, exothermic, endothermic. We've talked about some of these before, but some new concepts. You need to know what the heat of solution is, okay, and make sure you get a robust definition of that, okay. Entropy, everybody's favorite topic, the result of the fall, maybe. I recommend you do not use that definition on the quiz because it will not be appropriately full credit. You need to talk about Gibbs free energy. You need to know which way natural processes like to go. Okay. You need to understand what's going on in these pictures. Okay, there might be some questions about that. You won't have to solve anything with this. Like I said, I love to have math, but this is too abstract, and it's not helpful for me to have you solve those right now. You can do that in your AP chemistry class, I guess, that maybe we'll have in 3 or 4 years, who knows? Or 3 or 4 years, you'll all be gone. 2 years, who knows? You need to know what strong electrolyte, weak electrolyte, and if I didn't say it, what an electrolyte generally is. You need to know what this means. Why is it written like that? Okay, why are there a forward arrow and a back arrow? Okay, because this is an equilibrium. Okay, it goes through why we use what we do in there. Okay, note this: HCl aqueous goes to H+. That's an ion and an ion, and they're both in the aqueous form. Okay, so you need to be able to reproduce that. Should I ask you what happens when something like that gets in the water? Okay. Talk about saturation, what that means. Okay. I haven't decided whether we're going to do a lot with this yet. If you have to do something with this, it will be a question like one of these. Okay. Which just shows you can use a table. We read through that the other day. Okay, you know what? You need to know that like dissolves like in polar and nonpolar. Excuse me. There we go. Like dissolves like in polar and nonpolar. You know that alcohols are twice as volatile as water, meaning they're kind of flammable. That they're miscible in water. They completely dissolve 100%. They mix completely. Metal alloys are a solution of solids. Okay. I think we already had some of this, so I'm not going to ask you a whole lot about that. Do want you to know what saponification is. All right. You need to know what brass is, just because that's a good fact to know for your life. You need to know the general trends here in solubility as they relate, ionic solubility as they relate to temperature. Okay. And then let's talk about solubility of gases, strongly affected by pressure. Think of a Coke can opening, and that will help you remember exactly what goes on there. We've got the word effervescing, which means fizzing, right over here on the page. It's right off camera there. Make sure you know that. All right, that's that. Okay. I need you to be able to answer some questions. There'll be maybe some fill in the blank, some definitions. I really want to have y'all familiar with that vocab because it's so useful for future stuff. Okay. All right. I think that's that. Y'all just really, put in a couple hours of studying on that so that you can just do really well on that. Okay. There's no reason not to at that point. All right. So let's roll on to 10.3. All right, 10.3. All right, so what have we got here? All right, so we kind of think of sort of the word concentration, or let's just say concentrated. Okay, but think of it kind of as like something's more than it would normally be. So like concentrated orange juice is more concentrated than the way you normally drink orange juice, right? It's got more of the orange juiciness in it and less just water, right? Okay, well, obviously that's not a very scientific way to go about talking about concentration. So we have a number of different ways that we discuss concentration. Okay, and I want to talk about some of these. Let's talk about generally, just so you guys kind of know what we're. I had this open here in my other little book. Where is this? There we go. All right, I thought this was a good little note right here. All right, so we got a bunch of different ways, and we're only going to work with 2 or 3 of these, okay? But I do want you to be aware of what some of these other things. All right, so mass of solute per mass of solution. Okay, so that's what we were working on. Wait, per mass of solution. No, that's not what we were working with. Okay, because that's mass of solute per mass of the whole solution. Okay, so if I have, we'll switch back and forth a little bit here. Okay, so if we have 100 grams of sugar in 1,000 grams of solution, what's that actually mean? That means we've only got 900 grams of water. Okay? So that's very different than 100 grams of sugar in 1,000 grams of water. Okay? All right, so we had a volume of solute per volume of solution. Okay, that's not crazy either. We have milliliters per milliliter, or milliliters per liter, or something like that. Mass of solute per volume of solvent. Okay, I'm told this is used for often like steam or gases or something like that. I haven't used a whole lot of that. Mass of solute per mass of solvent. Okay, and that's what we were doing. We had grams of solute per 100 grams of H2O, which is the solvent. So that's what you did your homework in. Okay. All right. Then we have these 2 ones right here. He calls them very dilute solutions. Now it is mass per mass, so it's parts per million parts. Okay. And parts per billion parts. Okay. But when you're talking about things like arsenic or mercury or tetrachloride or something like that that's in the environment that doesn't need to be there, that's either a cancer-causing agent or something that affects taste or color, you don't have to have very much of it for it to be a major thing. So a dilute, quote unquote dilute, um, you know, is a relative term. Okay, so often heavy metals are measured in the parts per million, and then there are other sort of cancer-causing agents that are never supposed to be in a drinking water supply, for example, that are measured in the parts per billion in the things that are allowed. We have a Department of Health, that's a state agency that is under the EPA, which is the federal agency, to enforce drinking water standards. So that's what makes sure the water you drink is clean and really gets the cities or counties or water supply districts or whatever in major trouble if they don't do what they're supposed to do with keeping that water clean. So just wanted y'all to know that those are out there, parts per million and parts per billion. Anyway, that's that. And then there was, all right, and then we end up finally at the most common one, which is mass solute per volume of total solution. Okay, now why would this be useful? Well, it's useful because it lets you measure out lets you measure out, what's a spoon? You got to label your pictures. You know you're not doing a very good job. Okay. All right. So what you can do is you can measure out 10 grams. We'll put it down here, and then fill this to the 1 liter mark. Okay. Like exactly. And then you know how much mass you got in there and then how much the volume of the solution is, because it's exactly 1 liter. So it's sort of an ease of chemistry performance issues and not so much one that makes all of your calculations a whole lot easier. Because that doesn't really help us a whole lot to know like what the exact ratio of these atoms or moles is to these moles, because that solution, these grams are taking up part of that volume. And when it's 10 grams per 1 liter, it doesn't really matter that much. But what if it was 510 grams? You can see how that would have a pretty significant volume. Okay, so that doesn't really tell us like per 100 grams of water how many grams or moles of this solute. We'll call it sugar again. How many, what that exact ratio is, but you do know that if you've got, in addition to this preparation thing here, we also know, think about this. What if we just talked about calories per 20-ounce Coke? Okay, it doesn't tell you how much of that, and we could think of this as sugar per 20-ounce Coke, right? We know that, we want to know that if I drink that 20 ounces, how many calories or grams of sugar or whatever it is I'm getting. Well, it wouldn't help for you to tell me, think about how awkward that would be. Is like, all right, I'm drinking 20 ounces of Coke, and I know per 20 ounces of water, I get 40 calories. But in this Coke, that sugar takes up some of it, so it's really only 18.5 ounces of water to make up this Coke. So you want to know 20 ounces of Coke gives you X number of calories or X number of grams of sugar. Okay? So it's kind of a two thing. Ease, it makes the solutions a little bit easier to prepare, and if you're sort of filling to that, and then it makes it easier to deliver very specific amounts. All right. So this is called molarity, and it's represented by a capital M. Okay, and it is the moles of solute over solution volume. And we'll say that this is typically liters. That's how we're going to work with it. Okay. All right, so that's that one. And we're just going to introduce them both right now. Okay. And then the other one is molality. So molarity, molality. And this is little m. That's a terrible little m. Okay. And I think it's supposed to be italicized. That's really hard to do by hand, so y'all get over it. Okay, I assume you're following along in your book so you can see that. Okay, and so that's, again, note that all this is in moles. Okay, we don't, neither one of these has anything to do with grams. It's always going to do with moles. Okay, and then this is in solvent mass, and that's per kilogram. Okay, and I think this actually talks about which one's useful where. Maybe not. Oh, maybe he talks about it. So molarity. Okay. Maybe y'all can find it. You can usually find those things better than I can when I'm trying to find it right here on the fly. Okay. All right. So basically, you know pretty quickly from your problem which is which. Although sometimes you can be asked to convert from one to the other. Okay. And so he points out that you have density equal to mass over volume. Okay, this is density. So lowercase rho, R-H-O. All right, so if you've got a mass and a volume you've got to get from one to the other, you have density tables that you can use. I think he provides one for water at different temperatures. I'm not correct. If I'm not correct, sheesh. If I'm not mistaken. Well, I thought he had one. I thought I saw that. Once again, sheesh. Well, you'd always be provided with something like that. You never have to memorize anything like that. Okay, well, you know, water is pretty close to always the same density, but it does change a little bit with temperature. So we always need to be aware of that. So you could be given a density of any fluid, and you could convert that into a solution volume. And usually the volume itself of the solute, you know, if we're adding 10 grams of salt, because of the way the molecules sort of you know, get in between one another, it doesn't necessarily add that volume to the solid to the solution. Okay, so if we added 100 grams of salt, that might not take up all that much volume. So I am pretty sure we will always, well, it'll be clear whether you're supposed to assume that or not. And also, it may be always a prepared solution. I'll have to make sure I write my questions carefully so that's clear to you, so we don't have what happened on the last quiz, which is badly written questions, or last test rather. All right, so let's look at some of these. I want us to be pretty good at some of these. So let's just kind of work through and talk and see what we've got here as far as examples, okay? So this chemist needs 50 grams. We're just going to work through 10-4 here. Potassium chromate. All right. For reaction, she only has 4.5 liters of 8 molar. Notice that capital M there. K2CrO4. Okay. So what volume does she need to get that 50 grams? Okay, so what's the first thing we've got to do? Well, the only thing we've got is a molarity here, which is moles of solute for a solution volume. Okay, and so we know that molarity is equal to moles over liters of solution. Okay. All right, so we just plug in here. Well, first of all, we got to figure out how many moles do we need. Okay, so we say 50 grams potassium chromate. And then we have what? X grams down here, so we'll have 1 mole up here. All right, and then what is our molar mass there? Thankfully, been worked out for us. Obviously, we would just add those up from the periodic table. And what does that equal? We take 50 and divide it by 194.19, and we get 0.26 moles. Okay, of K2CrO4. All right, so this, again, this calculation is never going away, okay? You'll need to be always on the lookout for that. All right, so that's how many moles we need. All right, so now we can plug that in here. We're looking for what? Volume, which is our liters. So I'll just put an X there. How many moles do we need? We need 0.26 moles. And what goes over here? What's this? That's molarity. So that's 8M, 8 molar. All right, so just for the sake of the fact that I still see some mistakes on the algebra here, multiply both sides by X. This cancels out. And we divide both sides by 8. We end up with X is equal to 0.26 over 8. Okay. And it ends up being 0.032 liters of solution. Okay. And you shouldn't have to worry about any conversions as long as you kind of made sure you were in the right units to begin with. Okay. And you can double check that. Just take that and multiply it by your concentration, and then make sure that they multiply out to be what you need right here. Okay, so super straightforward. Super straightforward there. All right. And let's just work one the next kind here in example 10.5. Okay, so a 0.3 molality solution of C12H22O11 is prepared with 0.75 liters of water. All right, there you go. All right, so what do we need? So molality is equal to the mass solvent, the mass of the, darn it, solvent. Sheesh, I'm a mess here. I'm sorry, guys. Moles of solute of the mass of solvent. So we got a couple things we got to do here, right? All right, so we've got to get this to mass. All right, and we got to get we got to figure out the number of moles we need of this. All right, and we're looking because we got to get moles, and then we got to go to grams because it asks us how many grams do we need, how much mass is sucrose present. Okay, so we'll say 3.0 little m. We know that's some number of moles. All right, mass of solvent. How do we do that? So 0.75 liters, 1 kilogram per 1 liter. And we're just assuming it's at, let's see, what does this say? Okay, well, no, we're not. We're assuming 0.998 kilograms per liter. All right. Which is also the same as grams per milliliter, because a gram is 1,000th of a kilogram and a milliliter is 1,000th of a liter. So we'll say that that is, we got 0.75 times 0.998, and we end up with 0.749 kilograms H2O. All right, so now we multiply both sides. Right. And then we end up with 2.25 moles C12H22O11. So now what do? We convert that, right? 2.25 moles CHO. I'm going to shorten that. All right, so we know that 1 mole CHO, that's 122211, of course, and then we've got a mass of 342.3 grams per 1 mole. We multiply that through and we would know that there are 770 grams. Okay, so basically it all comes back to knowing this and then figuring out how to plug these values into there. Okay, so make sure you know those equations, like it appears that I don't. And just be careful. One is moles of solute over mass of solvent, and one is moles of solute over solution volume. Okay, so they're identical except for this bottom part. Okay. And you need to know which one is called which. Okay? All right, so that is 10.3 right there. So I would suggest you guys as a class, I assigned you 17 and 18, And I'm actually going to change this here in just a second. But I think part of our issues on working problems is, I hate to say it, don't ask you to work enough. So I am going to look at our homework assignment. I'm going to expand it just a little bit to give you guys a little bit closer to maybe a half an hour or 40 minutes of problem solving rather than the 10 or 12 that I think these two are going to take you. So probably adding 2 there, and I'm going to get you guys, when I finish this video, I'm going to send to Mrs. Barron 2 other problems for y'all to work in class to make sure you guys understand the process, and I'll update your homework assignment. So and send an email. I will note it in the email I send to her, and she can write it on the board here in just a second. Okay, so y'all turn me off. If you haven't already, pause me, finish your solubility curve review, and then work a couple of these problems together in class, and we will get together on Thursday after you take your quiz. All right, study up on that. Bye.